Thanks for inviting me here, Hans. I appreciate the opportunity to address this symposium. As Hans said, I'm Matt Richards. I used to work for General Atomics for about 28 years, mostly on gas-cooled reactor design, technology development, and other aspects. And starting in 2012, I started working for Ultrasafe Nuclear Corporation. Keep in mind about HTGRs is that their design features are well suited for a significant expansion of nuclear energy. And we've talked about the passive safety with no active safety systems required. Our goal is no public evacuation required. The goal is competitive economics, and I'll talk more about how we can get there later in the presentation. These reactors operate with high thermal efficiency, about 40% for a steam cycle, approaching 50% if you go to a direct gas turbine. They have siting flexibility because they have lower waste heat rejection and reduced water cooling requirements. Again, the flexible energy outputs with electricity, hydrogen, processed steam, synfuels, et cetera. And another thing to consider is that these reactors have very flexible fuel cycles. We have LEU designs, Fort St. Vrain, THTR with HEU. There have been demonstrations of burning essentially weapons-grade plutonium down to very low levels with this coated particle design, as well as thorium utilization, which has been demonstrated again in THTR and Fort St. Vrain. These are just some concepts here. This is the Japan Atomic Energy Agency. They call GT HTR 300C. That's cogeneration of electricity and hydrogen, so heat comes off of this heat exchanger to a hydrogen production plant. And that's just an illustration of what the design would look like. This is the General Atomics gas turbine modular helium reactor. This is a direct cycle gas turbine. What comes out of this machine here is electricity directly. So that's another potential way of improving the economics. And we talk about inherent safety. I think it's important to try to define what that means. What are the requirements for inherent safety? And these are just three that I came up with. That's making a core meltdown physically impossible, regardless of accident severity. Relying only on laws of nature and passive, inherently safe design features to prevent a core meltdown and achieve safe shutdown conditions. And again, no public evacuation required because of radioactivity released during any accident, regardless of severity. And so that led to these design features, of course, the coated particle fuel that we've been talking about this week. The annular graphite core illustrated here has very high heat capacity. It also enhances the heat transfer rate and limits the temperatures during loss of coolant accidents. And then there's very low power density that helps maintain acceptable temperatures during normal operation accidents. And then the helium coolant is inert, and that eliminates corrosion considerations and reduces circulating and plate out activities. We talked a little bit about how we define our radionuclide design criteria, but basically we go from outside in. We start with the top level regulatory criteria, like 10 CFR 20, 50, as well as the EPA protective action guidelines. And so then that defines the requirements for the various barriers, including the building, the primary circuit, and the various components of the fuel, which is the graphite, the matrix. But the most important barrier, the one we rely on the most, is the fuel. And we're counting on the fuel even after a hypothetical accident having failure fractions on the order of 10 to minus 5, 10 to minus 4 range. And I won't go into detail on this. I think we've had a lot of talk about what the licensing approach is, but basically it's a risk-informed, performance-based licensing approach, defining event frequencies as a function of dose requirements, and utilizing, importantly, what's called the mechanistic source term, that takes advantage of the good performance of the fuel, so that you don't have a prescribed source term like you do for other light water reactor concepts. So now I want to get into what are some of the economic impacts of various inherent safety features. And you talk about first starting with the TRISO fuel. And one can argue that TRISO fuel is the real accident-tolerant fuel. We have these accident-tolerant fuel programs, but that this is the real accident-tolerant fuel. And, you know, it's been demonstrated, you know, in all these recent heat-up tests to achieve that goal. Of course, it's more expensive to manufacture on a unit heavy metal basis, but it has much higher burnup capability, including for some concepts we call deep burn applications. We can go to very, very high burnup. So that can help reduce, offset some of these higher unit manufacturing costs. It's also highly resistance to corrosion in a repository environment. And so that makes it a good component for a permanent geological disposal. So in essence, the primary containment barrier for the waste package is created when the fuel is manufactured. So this will help reduce some of the back-end fuel costs. And these are just some simple calculations that were performed for triso particles in a repository condition. Over time, you build up radiogenic helium, so that will increase the internal pressure. And then dry conditions, even out to 1 million years, have very low failure rate. Even if you assume the repository is flooded, permanently flooded, at 1 million years, the failure fraction is 10 to the minus 4. And as I mentioned, you know, as we mentioned several times today, it provides the primary containment of radionuclides during normal operation accidents. And this can help enable reducing costs in other parts of the design. For example, requirements on the helium pressure boundary in the reactor building. So what are some of the impacts, economic impacts on the core design? Well, we start with this annular core design. It has relatively low power density, but that's going to cause you to increase your core diameter and your vessel diameter. And then because of that, as Lou mentioned, the module power rates are limited to something in the 600 to 700 megawatt range, because eventually this vessel size diameter gets too large that is within realistic capabilities of manufacturing. Of course, we have inert helium coolant, which helps reduce the circulating and plate out activity. But, you know, helium as a gas is less efficient than water or liquid metals or salts, you know, for transferring heat. So that further limits your allowable power density. But the thing to keep in mind is during the accident, you have this very, very slow response, very slow transient. So you have a lot of time here while this heat up is occurring. And one of the things I'll talk about later is that because of this transient temperature response, you don't want a high pressure in your reactor building as a driving force to get what little radionuclides that do get into the building to drive them out. So I like to talk about how inherent safety features can benefit economics. Of course, we talked about the triso fuel and offsetting the manufacturing costs with high burnup capability, plus adding flexibility to the fuel cycle. Of course, with the HTR, you have what's a relatively small module thermal power combined with a relatively large reactor pressure vessel. But what you get with this design is you have no active safety systems required. The only safety system you have is a passive reactor cavity cooling system. And it's a relatively simple design, and you can argue that it's mainly there for investment protection and not so much for public safety. And so you have minimum requirements on the reactor building design for radionuclide containment. And so the VLPC enhances the safe response for slow heat up transients because there's no pressure driving force for release. So we're not saying we can use a VLPC because we can get away with it. We're saying we can use it because it helps the safety case. But another thing that we did recently, we did a project with Ultra Safe Nuclear, Framatome, and Texas A&M, looking at how a reactor building, VLPC building, would respond during a depressurization event. We did both analyses and experiments with the scale facility, and there's a poster session in the lobby on that. And what we found, both analyses and experiments, is that the building during these depressurization events, you have about 5 times the molar volume of helium in the helium pressure boundary than you do have air in the relatively small compartments within the building. So when you do have a break in the helium pressure boundary, you end up flushing out essentially all the air in most parts of the building. This is the black line here is the reactor cavity, and you can see it essentially goes to 0 and stays that way for at least a day or so. And even if we do assume 100% error, all the previous accident scenarios analyses showed negligible safety consequences. So now I want to get into what are some of the barriers to deployment for advanced reactors, and specifically looking at ones that are the furthest along, the MHR and the sodium fast reactor. And you can argue that the R&D is pretty much essentially complete for those concepts. But to get to an FOK plant, you still need to do final design, licensing, construction, and that's going to cost you on the order of $3 billion based on several different cost estimates, including ones done by the NGMP Alliance. And so the business plan has to justify this first-of-a-kind cost. And what we've seen, because there's no reactors deployed, obviously, is that it's too risky for private industry alone. And in reality, any advanced reactor deployment is going to depend on strong and lasting government support. Historically, we did that in the US, and in China, HTRPM is an example of that type of support. Of course, in the US, another example is low fossil fuel prices. Right now, there are no carbon subsidies for nuclear energy. As Dennis mentioned in his presentation, we can start to compete when the natural gas price is in the $6 to $8 million per million BTU, which happens around based on this prediction, around the 2030 timeframe. But are you going to risk $3 billion on the hopes that this curve is going to stay that way? Probably not, right? But there are places where fossil fuel prices are significantly higher outside the US. For example, Japan and Korea are the top 2 importers of liquefied natural gas, which of course that adds a lot to the cost. And the European Union costs are also significantly higher. So that leads to looking at, can international markets be an initial focus for commercial deployment? And can this support the case for a demonstration plant in the US with the NRC licensing pedigree for the global markets? And so the NGMP Alliance actually started looking at that as part of various studies that were sponsored by DOE over the last few years. And so how can international collaboration overcome the deployment barriers? Well, it'll add some geopolitical justification for deployment of a demonstration plant in the US with this NRC licensing pedigree. It could save funding for the individual countries, especially if you're focused on a common design with shared technology development. But it needs a lot of political support in all the countries involved. Now, the NGMP Alliance, we established relationships with Poland, European Union, Japan, and Korea. There was a common interest in the prismatic block concept, industrial process heat, and hydrogen production. But, as Dennis emphasized, any of these international collaborations have to be properly crafted to avoid the complexities that could come up, like the requirements for the work share, intellectual property access, deployment rights in respective countries, regions, as well as the overall project governance. There are a couple of ongoing efforts. One is PRIME, which is called the Polygeneration Reactor with Inherent Safety, Modularity, and Economic Competitiveness. That's kind of a mouthful. But this includes the NGMP Alliance, Poland, Japan, JAEA, Korea, CARI, and EU governments and institutions. It builds upon the European Nuclear Cogeneration Industrial Initiative, and it's aligned with the recent EU Gemini Plus and MR proposal objectives, and those included define the design basis for a reference cogeneration MHR, demonstration of MHR cogeneration at a specified European industrial site, and then more recently, Poland has shown a strong interest in utilizing MHRs for providing electricity and process steam for industrial applications. So this could be a candidate location for the European site, European demonstration plant. And Poland has been doing some studies on their own as to where they could deploy MHRs at chemical plants. And this just shows 13 of their largest chemical plants with about 6,500 megawatts of heat requirement in the temperature range that the steam cycle gas-cooled reactor can provide. And based on their studies, they thought reactor modules in the 200 to 350 megawatt thermal size would fit the need. As part of the work done by the NGMP Alliance, we also did a siting study. We looked at 4 candidate sites, including this Portsmouth site located near Piketon, Ohio. It was the site that scored the highest in our evaluation of these sites. And this is a former uranium enrichment facility. There's an organization called the Southern Ohio Diversification Initiative. They've already been working with DOE to try to work to reindustrialize that site. It has a fully industrialized nuclear reservation. It's about 3,700 acres of land owned by the DOE. There's lots of existing infrastructure. As an enrichment facility, they at least have some experience with NRC licensing. And there's very strong local public and political support. As I mentioned, this was evaluated as part of the study done by the Alliance. We'll look at one other way, and this gets into some of my company's specific activities about how we can, break these deployment barriers. And one thing to look at is remote locations. And can the economics be favorable for small, and I mean very small reactors at remote locations? So we're talking about applications that are off the grid, that require very expensive transportation of diesel or other fossil fuels. And so what are the requirements for that? Of course, inherent safety, because you're going to have to probably integrate with industrial applications or a community that's relatively close by. You have to have very high reliability, availability. And most importantly, you need a market that justifies deployment of many nth-of-a-kind plants and attract investment. And if you do look at these remote locations, that's where you can start to see, at least initially, how you can meet this third requirement, which has been the biggest one, biggest barrier for deploying in the US. And so we developed this concept called the micro modular reactor, MMR, for these types of applications. It's based on the conventional steam cycle HTR technology with somewhat more benign operating conditions, a somewhat lower helium outlet temperature, and the primary helium pressure is about half that of the steam cycle HTR. And right now, it's a well-established project. It's currently undergoing vendor design review with the Canadian Nuclear Safety Commission. We're actually fairly far along with that review. And one thing that I was thinking about, this can be, trying to find a low-risk case to, for both deployment and the licensing approach for advanced reactors with inherent safety. So this could be a case where you test this risk-informed, performance-based approach with your mechanistic source terms. And trying to bridge that $3 billion gap, that $3 billion comes down now quite a bit because you have much lower capital costs than commercial scale reactors. And that can reduce your investment and licensing risk as well because your source term is also much smaller for this reactor concept. And I'm just going to quickly go over some advanced concepts that could help economics. I've talked about this a little bit already, the GTMHR. And because it eliminates a lot of these balance of plant systems and has high thermal efficiency, you could argue it's the most economically competitive SMR concept for electricity production right now. And it also can be adapted to produce processed steam and hydrogen production. And the thing I'll discuss a little bit is this reactor concept is also good for integrating with fast reactors if you're looking at breeding applications and more efficient actinide destruction. And this just illustrates, these systems that are eliminated if this goes from a steam generator to a gas turbine. So you eliminate the steam turbine, the feed water pumps, the piping, everything. And just to do a little comparison of, we did a comparison of the GTMHR versus LWR in terms of the areas of core, fuel, power conversion, safety systems, and containment building. And clearly, the high power density core gives the LWR the economics. This is what you're trying to fight to overcome. And one way, and also with the fuel being more expensive, but you try to take it to higher burnup to overcome the increased cost of fuel. When we start to get to the GTMHR, the power conversion, we start gaining on economics. The safety systems you gain on economics, and the containment building you gain on economics. And so the GTMHR, it starts with inherent safety and then tries to achieve competitive economics with compact, efficient power conversion and elimination of the active safety systems. And briefly discuss these fuel cycle applications, potential fuel cycle applications where you can use the gas-cooled reactor. This is part of a study I did when I was on assignment at Japan Atomic Energy Agency in 2007. And we're looking at the reference Japan sodium fast reactor operating with a breeding ratio of 1.2, producing the electricity requirements. And then the GT-HTR300C, the concept I showed earlier, which can be used for electricity, hydrogen, synfuels, process heat, et cetera. And so it could operate in two different modes we looked at. One was mixed oxide fuel, and the other was just direct use of the transuranics without blending it down with uranium. And so those were the burn-up ranges for those two. And we found that we could operate this system sustainably if we used the MOX option. About 20–25% of the thermal output was from the gas reactor. If we went to a deep burn option and added thorium, it would go up to about 40% of the thermal output from the gas reactor. Because the conversion ratio with the gas reactor using a high enriched fuel like true with thorium is about 0.7. And some people probably here remember the GNEP, the Global Nuclear Energy Partnership, that was using fast reactors, but operating them as what they call ABRs, advanced burner reactors. So this is breeding ratio less than 1. And this was the reference GNEP strategy normalized to 100 gigawatts electric. And it's showing various mass flows for that, including how much transuranic waste is produced. And we looked at what we call the two-tier GNEP strategy, where we put a VHTR in here operating in this deep burn mode, like the 600 gigawatt days per metric ton. Just one step pass through the reactor. And so now this split, instead of 68 LWR, 32 gigawatts electric for the fast reactor, we end up with about 70 for light water reactors, 20 for the gas reactor, and about 10 for the advanced burner reactor. But the key things to note is that the true waste is down, more than a factor of 3, from 800 tons per year to about 85 tons per year. And we don't have to do nearly as much recycle. We have 32 gigawatts of fast reactors versus 10. And the other thing to note is that the importance of reducing the true waste is it's the biggest heat load, long-term heat load component of the waste, and it actually is what determines the repository capacity. So I think that's all I had to talk about, so I'll be happy to take any questions.
Questions? Oh.
Will the Canadian safety regulator let you build your design and then have it as a demonstration where you could do demonstration by test to, do a blowdown event or something like that?
Yeah, I can't talk too much about what we're doing on that project because everything's proprietary right now. But like I said, we're fairly long. The vendor design review is like an optional step for vendors to get in good graces with the CNSC before they jump right into a full-blown, licensing effort. But we've had some talk about maybe building Chalk River or someplace like that, a demonstration module. But
one issue that we don't talk about, but you hit on it briefly here, was the waste form for the TRISO fuel for a typical prismatic reactor. How would that work? Would you separate the compacts from the block and put them in the repository, or what?
We've done a lot of studies on that, and I was the one at GA mostly involved with those studies, and we determined that actually the whole block is probably the best option. Oak Ridge also concluded that with one of their studies, because the graphite block is actually a nice container. It's also highly corrosion resistant, and you don't gain much, but you get about a factor of 5 separating the compacts out in terms of volume. But then you have to put those in some kind of container, and the repository space is determined by the heat load, so you're not gaining anything on reducing the heat load.
A pebble bed reactor, you just put the pebbles in as.
Yeah, Germans looked at that, just directly putting pebbles in the ground.
Others. All right, thanks, Matt.
All right, thanks.